Hi, good morning. Good morning. Less than 3 seconds. Today, I think I will give a overview and rephrase all the things I cover in last Wednesday. So yeah, about the hashing part. Yeah, it's related to your assignment 6 also. And then briefly cover the today I will really cover the graph. Graph. Yeah, the graph. I will introduce a graph today. Yeah. So then today after that Wednesdays I will cover the breadth search and depth search for graph. Actually, it's very similar. The idea is very similar to what you have learned in binary tree. Yeah, the just graph is a little tree is a special case of a graph. Then yeah, handling the breadth search and depth search in implementation, in whatever understanding the complexity of this, it is a little bit more complicated than the tree. Yeah, graph is more general. Yeah, so roughly this is this week plan. Yeah, then now is week 10. Week 11 and week 12 I will cover. Probably week 11 should be able to finish or maybe extend a bit. That's why today we can slow down a bit. Yeah, then week 11 will be cover. Next week we'll cover the some very classic problem like Queen problem. And then I also cover another one will be the maximum flow, matching problem and maximum flow. Probably will finish all the way from week 11 to week 12. Yeah, maybe week 12 Monday can we cover everything. Then week 12 I hope in my plan is like week 12 Wednesday will be give a overview summarize this whole course, and your lab test and revision everything, or any doubt during week 12 Wednesday should be able to finish all the lecture. Yeah. Then yeah, assignment. Yeah, later I wait for 10:30. Then more people coming in. Only 20 people. So far, any question? If you have any question, you can post it first. I see whether I can answer it first. So when we delete a key from the hash table, how do we mark it as delete? If you're talking about the assignment, I declare another variable, yeah, to as a marker for you to indicate whether the slot is used, deleted or empty, right? Yeah, if you're talking about in the practical way, I'm not too sure. I guess you in other, if it's talking about practical way, sometimes people may do those things through some hardware or using some hardware or something like that to use certain things to as a mark that this particular memory slot is already occupied by something or not occupied by something, or it's a deleted, it's an empty slot. Yeah, although the content the mem it's just like, I think if you observe some your some system, that's why a lot of people complaining that their program is working in their PC, not working in the hacker earth. The reason part of it is something like what you see here is the slot, that particular memory slot already deleted, but in certain system they don't really delete it, they still keep it, so that next time you go to the same memory location you will be able to retrieve the data. Yeah, because the data not really deleted. Yeah, these are the things like they depend different system, they may have some marker there. Yeah, then you trying to access, you go and look at it, the thing is still inside. Yeah, so in the hard disk, all this, your hard disk actually inside there are some this kind hash table for you to very quick to access certain data. Yeah, all these things are using the yeah hashing method to store the data, and for you to use the hashing approach to retrieve the data. Yeah, so sometimes marking if you're talking about practical way, marking the slot whether it's empty, not empty, deleted. Yeah, maybe some are using hardware through the hardware approach. But here, of course I cannot do that for your assignment. So I have to know way to. The best I can think out is I just declare another variable as a marker to indicate that this slot is occupied or not occupied. Okay. Uh, okay. 40 students. Is there any special case? Is there any special case to concern about in hash player? I think if you're talking about in the assignment, Tian Tianran who asking is about the hash table. I would say a few quite a number of, actually there's no very complicated, very tricky implementation in the assignment 6, but something you need to think about it is like when you delete a key, that slot is deleted. So-called that slot is deleted means that the slot is empty. The slot is empty. But the content, I didn't really physically remove the content, because remove it, I need to go and find the next prompt, yeah, to move them out. Then that is very difficult to do. So more practical way is just make a marker there, indicate this slot is already deleted. But behind maybe got some prompt. If you look, if you are trying to search the certain item, yeah, you may need to carry on your search. You cannot stop at the deleted item, deleted slot. Yeah, but if you encounter is an empty slot, yeah, then you can quite sure that behind no more already, no point to carry on. Yeah, that is the difference between deleted slot and empty slot. Because if you when you trying to prompt using the open addressing, when you reach certain point, you see there's a empty slot. You know that behind no more. Impossible. Yeah, there's in that particular search key is not a variable in this hash table. But when you reach certain point, which is a deleted slot, yeah, you won't compare it. But but you know that behind probably got maybe still have something, but you have to go and carry on your prawn journey to search. Yeah. So these are the things you need to consider. Yeah. And of course, I think if you think about it, yeah, these are quite a few cases, Yeah. So implementation, you need to take notes of. Yeah. Yeah, a lot of people having the runtime error in this and that. Yeah. So I find that over the week I probably learn more than you all, because you all, everyone trying to ask me to help them to debug. I think one thing I realize a few scenario. One is like you all don't like to use debugger to debug, or you don't know how to use debugger. Yeah. Yeah, that probably is not the very appropriate way. Secondly, you all like to use built-in function. That's when people write the code for you. Actually, it's not very good, especially at this stage. You are just learning programming. You already start using reuse people code, reuse people function, built-in function. Actually, you don't understand those built-in function. How does it work? I think it's good that's why although Hacker Earth allowed you to use, so I don't penalize those students. I let you use, but I strongly encourage you to build all the function by your own to fully understand it, because if you don't understand those things, you trying to just reuse next time. Yeah, just like what you encounter right now, when the thing not working, you have no idea why it's not working, because the function is not wrote by you. Yeah. So you don't understand, then you just trying to blindly use the function. In the long run, yeah, you will face this kind of issue, and the problem is get worse when you use more and more complicated built-in function. Yeah, you don't understand, you just blindly use, then you really only can blindly use. If it work, it work. It doesn't work, that's it. You can't do anything. Input to use code block debugger. I purposely let the code block able to work during the lab test. Yeah. So you should be able to use it during the lab test. Tag and empty index. Okay. For double hashing, we use hash1 key table. The first prompt. Yeah, normally, of course, for the double hash, for the linear, I think more problem in the, I thought it's a lot of problem in the close. Okay, maybe I go to the open addressing. Okay, here we introduce three open addressing approach. The first one is the linear probing. The second one, okay, linear probing. Okay, the second one is the quadratic probing. The third one is double hashing. So here we indicate the I. I indicate the I here. Yeah, of course, I didn't say that it start from zero. Of course, you have common sense. You want to. I thought it's common sense that we, of course, we start from 0, 1, 2, 3. Otherwise, how you implement a program and make it consistent? So the mathematics expression of the hash function is this. Yeah. But when you do the implementation, of course, you will start your I from 0 and then increase by 1, 2, 3. Yeah. So the next time you go in, after you insert the key in this manner, when you search, yeah, you also search in the same manner. You start from the 0. Then if the first location is not appropriate or it is already occupied, of course you will search for the next location, which is let the I go to 1, 2, 3, 4, 5, 6. And not surprising, you will stop at hash -1, because the next one will go back to the first position again. So that's why your prawn, you will work hash, depend your hash table size, between hash times. Yeah. So your prawn 1, 2, 3, 4, 5, 6 to hash. Yeah, same thing for the quadratic, same thing for the double hashing. Okay, so linear probing is the more straight way. Just like every time you just, this location is occupied, you just simply plus one, plus one, plus one. Yeah, until you find an empty slot. Then you just insert it. That's why it will causing the issue is about the primary clustering. Because every time you just increase by one, by one, by one, by one. Not surprising that certain area very easy to form a cluster. That's so-called primary clustering. Okay. Then yeah, so people think that linear not working. How about quadratic probing? So someone proposed quadratic probing. So this one is like they not only plus one plus certain I, they also plus I square. So same thing, I also start from 0, 1, 2, 3, 4, 5, 6, 7, 8. Yeah. But quadratic, yeah, a good choice is your hash table should be 2 power to n. Yeah. In fact, if you really go and try, I think some people asking me is about whether is it like other double hashing what you see later? Should I choose prime number? In fact, for quadratic, you find that you cannot choose prime number. If you really go and play around with it, you choose a prime number hash, and then you will find that no matter how you play it, yeah, you only can prone half of it. There's some in the number theory, there's some characteristic lah. I that's why I don't go and further illustrate this part. There's some mathematics can prove it that you only can at most search hash over 2 distinct prawn. That means only half of the slot you can visit. The other half, this hashing approach cannot let you reach those points. You only can reach half of it. Only when your h is 2 power to n and your C1, C2 is half. In that circumsystem, just like your n is 3, 2 power to 3, 8. Your hash table is 8. Yeah, in this circumsystem, you will find that your I equal to 1, you substitute in, I equal to 1, I equal to 1, so half plus half is 1. I equal to 2, then is 3, 2 times 2, 4, 4 times half, then 4 times half is 2, 2 plus 1 is 3, so it's 3. So you will find that it's, okay, and so on and so forth, 1, 3, 6, 2, 7, 5, 4. So you're able to 1, 2, 3, 4, 5, 6, 7. So you can expect that you're able to visit every slot. Yeah. But you'll find that if you choose your hash table as a prime number, you can go and try it out. I suggest you go and try one number, maybe 7, maybe 11, maybe 17. You'll find that you only can reach half of it. Yeah, no matter how you select your C1 and C2, yeah, you won't be able to go beyond than that. Yeah, there's some mathematics proof. I didn't show you because they are using some modular algebra to prove that it cannot more than half for other number, for prime number. Yeah, so that's why the table size in different, especially open addressing, the table size will need to carefully selected based on the probing approach you are using. If you're using linear, of course, no problem. Linear just plus one, plus one, plus one, plus one. Whatever table size, no issue. Quadratic, yeah, you better choose 2 power to n. Yeah. Then, same thing, you will find that although they don't have primary clustering, but you will find that every time you go to, if your initial prawn position is same position, yeah, then not surprising that every time you will move 1, 3, 6, 2, 7, 5, 4. So in somehow you will still form some kind of a secondary clustering. Yeah. Then that means every time you want to search certain key, you will first go to slot 3, then slot 4, then slot 3, slot 4, then slot 6, and so on and so forth. Yeah, every time. As long as the number first prawn is guide you to the position 3, hash you to the position 3, the next one you will be go to position 4, and then position 6, and so on and so forth. Yeah. So this pattern will keep repeat. Yeah, form some kind of a clustering. for double hashing we delete a key and insert the same key back. Do we insert yeah, as I said, double hashing or whatever hashing, as long as you delete the slot, you consider that slot now is already free, empty, available. So you're trying to insert the same key back to the hash table. If earlier you didn't do anything in between, then I would say that you definitely will go to the same location which you just deleted. And not surprising that, as I said, deleted slot is already empty. It is already empty, just you didn't really clear it, physically. So you of course you can insert it. Yeah, not only double hashing, any hashing approach. Yeah. So why is that? Okay, yeah. The Yan Kai question is what I trying to just now I want to set back to the close addressing. There's another one people asking about close addressing. Close addressing, you're talking about average case or successful are considered probability. I guess it's a lot of people. I think among these close addressing, I think the most difficult to understand is about this average case. When you're talking about average case, we're talking about that your hash table can be in any combination. It can be here got one slot, here got two slot, all the combination. Yeah, on average. Yeah, here got one slot, here got one slot. Can be one slot, can be two slot, can be three slot, all kind of that means I got n item. Imagine that I got n item. Yeah, I insert this n item equally likely hash into the hash slot. So it can be appear in the first slot, second slot, third slot, fourth slot, and so on and so forth. All kind of a combination are equally likely. All are possible. So, but one thing I'm quite clear is I got n item. Among these n item are equally likely. That means overall I got my hash table is h. The size I got h. The table size is h. Yeah, I got n item. So on average, each slot have, based on the log factor, each slot on average have n over h slot. Each slot have the linked list, the size of the linked list on average should be n over h. The size of the linked list is n over h. Okay, the worst case later I explain again. So unsuccessful search, that means the key is not inside this hash table. So on average, you will take, because on average, each slot have so many item need to search. After you search through n over h on average, then you can confirm that the key is not inside this hash table, right? So the complexity on average should be big theta alpha on average. Yeah. So that is unsuccessful search. After you understand this, the next one, successful search, is another. You need to imagine that you got n item. All these item can be in any slot. Can be here, can be there, can be in the first one, can be in the second one. You can have the first one got one slot, can be the first one got two slot, can be the first one got three slot, and so on and so forth. All kind of a combination. So successful search, you need to imagine that this particular successful search, that means the item is there. This particular item you want to search is not insert into the hash table. So if the thing is not inside the hash table, that means the rest should be you should have let's say it's the n item, then I should have n minus 1 over h item to search. And on average in each slot. I should explain one more time. So this thing, you need to think that, you trying to search. Okay, I have a hash table. The table size is hash. Then, each location there are some item. On average, there are n over h item in each linked list on average. Doesn't mean it definitely n over h, on average only. Sometimes can be 1, can be 2, then some may be more, some may be a little bit lesser. But and all kind of combination on average. I need to consider all the scenario. So some may be shorter. Then how do I think should not have any issue to handle the unsuccessful search. The problem is like successful search. Successful search, that means you need to think that you haven't insert that item. So all the search is before you insert this particular item. The scenario you trying to search, unsuccessful search, when the item is not insert into the hash table first, then the next moment you search the item. This one need to think. Let's say I got initially the I item. So the I item, that means the first one is like, if the successful search can be first time you search an item, it can be second time you search an item, it can be third time you search an item, it can be 4, 5, 6, to n item. So imagine the first one. So what does it mean is like, first one, if currently what is the successful search on average for the first time you search the item? You can imagine that this first item is not inserted yet. That means this hash table now is empty. So on average, of course you take 0. On average, that means right now this is nothing. So on average is 0. So I minus 1 over h on average. I is first. I is 1. When I is 1. So I minus 1 over h. So it's 0 over h. So on average, makes sense. Then after that, after you do 0 unsuccessful search, then the next one is the one you just insert in. This is the item you look for. You search it. So this is the average successful search when the item is the first item. When your search item is first item. If my search item is the second item, on average, my successful search will take how much successful comparison. How many comparison? That means if it's a second one, that means on average, I need to think that this hash table on average there are one item. There are one item. On average, can be here, can be there, can be any location. Then on average, only one item. So only one item is 1 over h. Then the next moment, I add one more. Maybe here, maybe here, maybe here. That is the second item I look for. So the second item I look for, just plus one more. So it's like you find that it's like you want to calculate the average search, average number of comparison done on the I items search. Is you trying to have an unsuccessful search on I minus 1 item. On average, I minus 1 item unsuccessful search plus 1. The next one will be the one you search successfully. That's why you come out this plus 1. 1 plus I minus 1 over h. When I item is sought for, the number of comparison is I plus I minus 1 over h. So on average, you need to consider all the item. First item, second item, third item, fourth item, fifth item, and so on and so forth. So you just sum it up. So that is a summation. I plus, 1 plus I minus 1 over h. I can be 1 to n. Then, each can be first item, can be second item. They are equally, they have equal chance. So it's 1 over n. Yeah, so that's why after you derive, in the end is 1 plus alpha. Then some student ask me, is it the 1, is it necessary? Because here we keep the 1, it's just trying to show you that, yeah, the average is like I minus 1 over H plus 1 additional search. You just want to express that, yeah, I got 1 more extra comparison. Of course, you write this one is in big theta alpha also can. Then some people are asking is like, what happen if H is fixed, is a constant, or N is proportional to H, or N is proportional to H, or H is a constant. Yeah, can I just write big theta N, or can I write big theta 1? Yeah. You after you make further assumption, of course you can further simplify. Yeah, but this one is more general expression. So if you make any further assumption that H is constant, N is proportional to H, all this, of course you can further simplify your expression. That's no problem. Okay. Yeah. So that is the searching times for successful search. Then just now the worst case unsuccessful search. If we have n item in the hash table of size h, the worst case will be 1 slot of hash table being occupied. We have n item in the hash table size. The worst case be 1 slot of the hash table be occupied. Then the successful search will be no, here is considered the worst case scenario. That means worst case scenario is like you have all your n item, don't know why, they all of them squeeze into one linked list. That means the worst case scenario, the most terrible scenario is like all your key is just insert just like a linked list. Your hash table totally useless. Yeah, no, didn't help you anything. It's just like all the key, don't know why they all insert into the same slot and then along the whole linked list. So when you do the unsuccessful search, I think no problem. Yeah, you need to search n time. Then successful search for each item. There is successful search. That means the item is inside the hash table. In fact, it's inside the linked list. Inside the linked list, it can be the first item, can be second item, can be third item, can be fourth item. But all of them are worst case scenario. That means all of them are in the same linked list. Yeah, you only consider this particular scenario. All the item is in the same linked list. Only one linked list in the hash table. In this hash table, only one linked list. And all the items squeeze into that particular linked list. And then every time, not surprising that every time you search, it's like first item, 1 search, second item, 2 search. Yeah, 2 comparison. Third item, 3 comparison, and so on and so forth. So average for this worst case scenario, yeah, or what is the expected value? Yeah, which is this. So same as the yeah, actually it's a linked list. So not surprising that it's just like the linear search you learned earlier. Yeah, so it's big theta n in the worst case. Okay, so this is the close addressing. I think something you need to think about it is this part. Yeah, it's a little bit tricky. Then hashing already explained. Linear is the easiest one. Yeah, of course, easiest one you expect that, yeah, there's a primary clustering or other issue, but implementation maybe probably is the easiest one. Yeah, complexity also easier to analyze. This one, yeah, having the issue, yeah, it didn't help too much because after you declare this thing, you still got the clustering issue. Yeah, you introduce a square probing, but it didn't really resolve the problem, and it make you harder to search the design the hash table. The hash table sites need to be careful. Select, yeah, because most of the times you only can have half distinct prompt. So this thing need to take notes on this. So you will form the secondary clustering issue. This thing need to take notes. Then double hashing. A few things common mistake is like, first is like this thing, the increment, the second hash function, this dk, you only need to do it one times. K is just the given key at the beginning. You just do one times. Once you decide the prompt is every time increase 3, or every time increase 6, or every time increase 5, the increment hash function will fix in this particular number. So and different number will get different increment. That will make their probing is unique. More, that's why it's a kind of a random probing, because you find that even you go to the same slot, different number will their probing approach, the number increment is different. Yes, technically close addressing hashing, you have unlimited slot because it's a linked list. But open addressing got the limitation. But you will make, but open addressing is like you just declare an implementation. The data structure is relatively simple. Because just an array, that's it. But open addressing, you need an array, and then followed by behind got a bunch of linked lists here and there, some long, some short. You also cannot just simply declare a 2D array to resolve the problem. So open addressing in terms of implementation is easier, but it gives you more problem. Like all these things, clustering issue, or your double hashing, all this, you got, and also the slot limitation. You don't have the unlimited slot. So soon and also the delete is a problem. Rehashing is a problem, which I'm in the next few slides will tell you. So when you trying to prompt, you find that every time, starting not clear. When you insert 11 to here, which is already occupied by 4 in the 4th position, they were trying to calculate this. You can see that I substitute is 11. So there's been no point to calculate multiple times. This thing just need to do one times. Once you decides, once you do this calculation, you find that the result is equal to 11 mod 3 is 2. 2 plus 1 is 3. So it's 3. That means every time I just increase my move 1, 2, 3. Next time will be 1, 2, 3. So will be here. Then here is empty slot, and I insert it. If it is not empty, I will carry on my journey. And if you look at it, since this is the prime number, why I select it as a prime number? You find that whatever this number, is 3 or 4 or 5 or 6 or 7, you can ensure that you will visit every slot eventually after hash time. So your I start from 0 to hash minus 1. You definitely can visit every slot. But if today my table size is even number, for example, even number, save my times. Here got 7 slot. I add one more slot, become 8 slot. When it's 8 slot, and let's say my dk is equal to 2. Some number, not this number, just example. Another number, another hash table, even number hash table. Then my dk is 2. I start from here. That's it. Then the next one is plus 2. I will go to here. The next one, let's say it's occupied. The next prompt will go to here. The next prompt will go to here. The next prompt, you will find that you start return back to the first position already. What does it imply? Imply that this position, this position, whether they are empty or not, you have no chance to visit them using the double hashing. Yeah, when your DK is 2 and your hash table is even number. Yeah, the first one you prompt, you consider the first one you prompt into that location. Then yeah, it's not a variable. You try the second one, which is let I equal to 1, I equal to 2, I equal to 3. Yeah, first prompt number, first, second, third. Yeah. Okay. So you can think about it. Why is prime number? Because prime number, yeah, what does it imply? Is imply that they're only divisible by 1 and itself. So whether your number is 2 or 3 or 4 or 5 or 6, you can go and try some prime number. Then I think in the one of the assignment I put 37. Why I have to put this kind of prime number? Yeah, because if I put non-prime number, and for example, if your table size is 9, your hash is equal to 9. Yeah, you have problem is like when your DK is equal to 3 or 6. Probably got all these have a problem. You find that you cannot visit every slot, empty slot. Yeah. Then that's in just like the quadratic probing will give you some problem. It will give you some problem that because you cannot visit every slot, empty slot. Then even the table is not full, you will consider it as full because you won't be able to reach there. Then what would count as error in double hashing delete function? And that error, I don't think if you encounter it, that's when your program already have some problem, because yeah, you can see that what I show you here, all this problem, you only need to prompt it hash times from 0 to hash minus 1. So you expect that you just need to do at most hash comparison. That's why every slot I already compare. Then what else? Why can I have some comparison more than that? Yeah, your table only got hash item. Yeah, the maximum you can have, because your load factor only can be equal to 1 maximum. Then no matter how you play this thing, it's not possible that you have more than hash comparison, right? So that's why I put error. But you should not see this output. Yeah, the purpose I put it there is for me to, when someone send me an email saying that their program got problem, that problem, I can go and take a look. Is it due to yeah, what is the reason? Maybe they already print something as it. Yeah, it just help you to debug, I would say. So if the slot is deleted, can we? Yeah, of course. That's why I said it's like when the key is deleted, we just like didn't physically really clean the slot. But whenever there's a new key coming in, they want to occupy this deleted slot, they are free to do that. And without any additional comparison, you don't need to compare this particular deleted slot is what is the number inside, because that is already deleted. That slot is already, the item is already deleted. So whenever you reach that there, you are free to insert it. But you need to think carefully. The number you insert, will it already exist somewhere behind? Yeah, because today you have one hash table. You maybe delete here. But your let's say I got one key is somewhere behind him. It's the next position, 42, let's say. Yeah, now I want to insert 42. Maybe I go to here, I go to here. Yeah, you said delete can insert. Delete is considered empty slot. Can I insert here? The answer is no. Because 42, if you want to try to insert 42, you have to check whether 42 is behind or not. It can be behind because this slot be deleted doesn't mean behind no more. It can be. It can be something also 42. You don't want to insert duplicate. You don't want end out that your whole hash table all are 42, right? Yeah, you no point to store the same number multiple times. So yeah, you need to check behind whether got 42 or not before you do the insertion. Yeah, and that also explain why that this garbage correction, yeah, is needed. When you have too many deleted key, yeah, you better do some garbage correction. Otherwise, yeah, your search, the number of comparison is still keep increasing even you already delete those key. Yeah. So I think this is the thing. The rest I think is like this. I didn't show you the proof. I just want you because the proof is a bit I'll say maybe a little bit. Actually, it's not too tough lah. If you're interested, you can go and check this book. Yeah, it's proved by this person, not Donald. He is the father of the analysis of algorithm. Yeah, it's a Turing Prize Award in 1973 or 74. Yeah, so one thing you need to know, I just want you to know is like all the time complexity is the function of this 1 over 1 minus alpha, 1 over 1 minus alpha. Yeah, of course, different hashing approach, their time complexity a little bit different. But they all are the function of this. Yeah. So the proof, maybe they need to use some, I see, originally I want to include it, but I find that they involve some series. Yeah, you may not learn. You're supposed to learn in year 1, but here I skip it. So if you want to know about it, you can go and study yourself. But well, in practice point of view, yeah, you just need to know that, yeah, this thing, when you're alpha, because for open addressing alpha maximum, that's when the table is full, is equal to 1. So not surprising that your successful search, unsuccessful search, yeah, will be when it is, yeah, normally it's close to alpha. So it's like you become infinity. When you close to, normally we wouldn't let it reach 1. Yeah, so we'll be getting increased exponentially somehow. Okay. Yeah, then of course open addressing, you got delete key issue, you got rehashing issue, because your table can be, yeah, after a while you will be full. So you need to create a bigger table to then update, and then you need to do like create a bigger table, like double the table size, and then the old data need to reinsert into the new table. So, and close addressing don't have this issue. Close addressing have the issue is like because it's a linked list. Yeah, if you didn't insert it properly, you will end up, or you design your hash table, your hash function, does not design properly, you will end up that your linked list all squeeze into one linked list, in just like the worst case scenario. And then end up is like you have a hash table, but it function like a linear search. Yeah, that is for the close addressing. For open addressing, the problem is like delete key is a problem. Rehashing is a problem. Yeah. Then probing, you need to ensure you visit every empty slot is a problem. Yeah. But all these things, yeah, when you implement, maybe you don't see too big issue. Yeah. It's just a hash function. You just call the hash function, and the hash function tell you the index. You just insert it accordingly. But when you design the hash table, yeah, when you decide to use the hash table, you design the size. All these things you need to understand how the open addressing work, and how you select the linear probing, quadratic probing, and double probing. How you select it is a problem. Okay, so this is all about your assignment 6 also. Yeah, it's not difficult, it's just like you need to consider a few scenario. Yeah. So this is the probing. Okay. Today one, actually, yeah, just start today one. The graph one. Okay, half an hour. Okay. So about today I just briefly introduce graph representation. Then Wednesday will be breadth-first search and depth-first search. So first give you some good news. So in that case, I think now it's already. I don't think I can cover the whole graph, everything by Wednesday, I guess. So what I'm going to do, like assignment 5, I think right now I only see how many, maybe only 100 students complete the assignment 5. I think, yeah, and I don't know why many students still have not logged in. I don't know what is the reason, but anyway, yeah, I don't want you to go and copy the answer here and there from your friend or from whatever. As I said, I will do the plagiarism check. So, and again, a lot of people keep asking me, yeah, once you get full marks, of course the following submission, they of course not surprising that they will just simply ignore. You already get full marks, you already get the highest mark, so they will choose I think before that, Dr. Owen already explained to you the platform, yeah, will take the first best attempt as your final as your final attempt, because you already get these highest marks. The following also get the same marks. I take the following one. Normally people will not after they get full marks, doesn't make sense why you need to submit further. So normally they just simply ignore lah, because it's the same marks. And I will not like last minute go and add a new test case to let you fail. Yeah, so you don't have to worry about it. Then third is another thing. They do have some limitation for the number of attempt, which is 300 attempt for one question. So you don't anyhow click, because they have to put this kind to protect their server. Otherwise, someone go and attacking their server, like endlessly submit. Because every time you submit one code, they need to compile and then check. Yeah, so evaluate all the test cases. So that will cost their computational power at the back end. So they need to protect their server. So they will limit you to have up to 300 attempts for every question. So try not to anyhow click. If you one click not working, yeah, you second click, there's no magic, same code, yeah, it should not give you different answer next time. Yeah, if they give you the different answer, one scenario I see is because you trying to access something out of the range. Like your array only got 10 elements. You keep trying to test or access the location in 11, index 11. Of course, no such thing. Yeah, index 10, not 0 to 9. So index 10. Of course, no such thing. So that memory location, sometimes it's 5, sometimes it's 6, sometimes it's 7, sometimes it's whatever funny things. Yes, every time you get different answer. It's just like every time you get the different wrong answer. Yeah, because you're not supposed to go and access something out of the range. Yeah, so this is something you need to take notes. Yeah, I think quite common. A lot of people, this one is very hard to debug, because in your computer, sometimes they allow you to access that particular memory location. In that memory location, just nice that it's empty, or somehow let you can terminate. But in their server, that particular slot, that particular memory location, which you're not supposed to go to access it, you trying to access it, then they give you some random number. Yeah, so that is what I see a lot of people having the problem. Their code in it got the bug. Yeah, it's not any different system issue. Yeah, they really got the bug. Just coincidentally that your PC give you a nice result that no error. Yeah, but that the bug is there. Once you change to another system, all the problem come out. Yeah. Then so later I will try to adjust the deadline for the assignment 5 and 6. Then what I can do is like, I think the graph I trying to combine to assignment 7 and 8 into one. Probably maybe Wednesday hopefully Wednesday I can release it. Okay, so maybe a little bit more question, maybe 4 or 5. Then the deadline I make it as around week 13. No choice. week 14 we're going to have a lab test. I don't want to keep extending to beyond the lab test 2. Okay, I want to make the lab test 2 as the final. If you want to extend further, then that is the next semester. Next semester week 13. So if you don't want, then better finish everything by week 13. And also I want you to have a break before the lab test, because you keep thinking particular algorithm, it's not very good. When I give you a new problem, a lot of time you very hard to solve it. A lot of time you learn these kind of things, this kind of algorithm programming, you find that it's like you're trying to learn it and then unlearn it and then relearn it. You need to trying to forget about all the things you have learned, and then trying to rearrange all these things, and then trying to learn how to solve the problem in real world in the future. So it's like learn, unlearn, and relearn. So I will try to release in these 2-3 days. I'm thinking whether 4 question or 5 question. I already got 3. I still thinking whether need to add another 1 or 2. Okay, so hopefully Wednesday I can release the last assignment, which is 7 and 8. So the weightage for the last one will be heavier. 7 and 8 will combine. Of course, more question. So, and you have more times to week 13. So that is the plan. I don't know it's good news or bad news. I think it's good news. They are using, I think they are using Docker, you are right. But that's why every time I see, sometimes I run someone got the problem is like every time they run, that particular illegal slot memory location can be any different number. So not surprising that some people complaining that they run multiple times on the same input. They give it return different number, because every time they will create different container, different environment to rerun the program. So those slots are unused. They may contain different number. Depend the memory they allocated. At that moment contain what number, and that number is not you create one. It's originally exists, because you're not supposed to touch that location. Your array is only 10 elements. How can you go to access 11 elements? So okay, another thing for the lab test wise, I think you also need to understand the assignment is for you to spend about 2 weeks. At least 2 weeks. The last one probably got, now is week 10, 11, 12, 13, 3 weeks. You have 3 week times, 21 days to do one assignment. Of course, I will plan to put the difficulty level much higher, because you have so much time to think, to discuss with your friend here and there, and then go and online get all kind of a resource or whatever you name it. So you even can send me the email and ask me, what is the issue here and there, ask me to check here and there. Of course, the difficulty level must be much higher. But if it's a lab test, the lab test 2 hours, you have MCQ and 3 programming question. Then that's mean average each programming question, you need to finish it in half an hour. Of course, I cannot set too difficult. I would say that definitely easier than your assignment, of course. But also, I would say that maybe not too easy that someone can finish it in half an hour or 5 minutes. Should be half an hour difficulty for average student. Because in the end, I want to come out a nice bell curve. I hope that can show the distinguish the good student, weak student, hardworking student and not hardworking student, this kind of thing in the distribution, to show you that where you are. So I would not set too difficult question that you not possible to finish in 1.5 hours for average student. Okay, so if you very easy question you still cannot do, maybe you have to stay back for 1 semester It's better than, because after this module is something very important. I have to emphasize, because after this level, yeah, we expect that you're already quite good in writing program. Yeah, give you an algorithm, you should be able to write out. Okay, so today, finally, after spending so much time, okay, I brief this week anyway. If cannot finish today, Wednesday we still have times. Yeah, the graph representation only. The breadth and depth will cover maybe Wednesday or next Monday. Yeah, we only left this few topic only. Yeah, so I think you should, I believe that those people, especially those people are taking discrete mathematics, they also tell you about the graph. Yeah, it's formed by a set of vertex and a set of edge. And then, yeah, let's say it can be called vertex. Some books call vertex, some book call nodes, and so on and so forth. Then here I represent the number of vertex as using this absolute notation, indicate the number of vertex. Then same thing for the edge. Yeah, it's a set of edge is trying to connect the vertex. Yeah, normally it's two vertex here. Yeah, of course you can sell this is the vertex, this is the vertex. The edge is the one which connect, they call edge arc or link, are the one connect these two vertex. Of course, some in graph you also can one vertex connect to itself. Yeah, but here the problem we discussed, we not considered this. Yeah, we only considered the edge connect between two vertex. Yeah, so the number of edge, the worst case scenario is like you have so many vertex, you only can have so many edge. Very easy to verify. If you have 4 vertex, the maximum number of edge you can have is first one connect to 3, the other 3. The second one will add another 2 more. Then this one will add 1 more. So the first one got 3 edge. The second one got 2 additional new edge. The last one got 1. Yeah, which is yeah, 6 yeah, which is V equal to 4. 4 times 3, 12 divided by 2, 6 So yeah, which is, you also can see this thing that is a VC2. You just select any, the edge is formed by link 2 vertex. So of course it's the number of vertex. You just select any 2, all the combination. Yeah. So when we and then the degree of vertex is the number of edge incident to it. So like this one, you have 1, 2, 3. The degree of vertex is 3. Yeah, this one also 3. All of them are 3. The degree of vertex is 3. You can see 1, 2, they have 3 edges. The number of edge incident to it. So, okay, so 3 is what you have learned in the first half. Is a special case, just I already mentioned. It's a special graph with no cycle. Like this one cannot call 3 because got cycle. Here got 1 cycle. Yeah, here got another cycle. There are quite a lot of cycle here and there. 3 is no cycle. That means this is a 3. This is a 3. This one is a 3. As long as it doesn't form any cycle. Yeah. So it is a 3. It's a special case. So not surprising that those things you can apply in 3, you can also apply in a graph. But not everything in a graph you can apply in a 3 because there's no cycle. So graph, there are a lot of type of graph. The one just now, all the graph I show you is undirected. It's also possible that we can add some weight on the edge. Each edge have some weightage. Yeah, you also can have directed graph. You also can combine both. I forgot. Yeah, you also can combine weighted and directed. Yeah, these two. That means on the directed graph, you can have each edge still have they also have some weight. Yeah. Then this is the complete graph. That means what you see, the maximum number of edge you can have. Yeah. Then that's called the complete graph. Yeah. Different problem, we will use different graph. Yeah. So if edge E is xy is an edge in an undirected graph, then E is incident with x and y, undirected. Yeah, so that means you have this thing. So this one, this is x, this is y, then this edge is E. Yeah, so it's EXY. That means this edge is trying to link x and y. So E is incident with x and y. Or x, you also can set x is adjacent to y, or y is adjacent to x. Yeah, if E is unordered, then G is undirected. If the edge is unordered, then G is undirected. Otherwise, G is directed. If E is an edge in a directed graph, then Y can reach from X through one edge. So target Y is adjacent to the source X. So directed graph, this is directed graph. Let's say this become a directed graph. Yeah, so Y can reach from X through one edge. Yeah, but doesn't mean that this same edge, of course, this is a directed. So that means you cannot use so target Y is adjacent to X, but you cannot set X is adjacent to Y because they only have one direction. You cannot go back to the other direction. Yeah, in this as a simple example. Is it similar? I'm not too sure. 1115, the maze, but path searching definitely is one of the typical graph problem. Yeah. So today just I introduce some terminology lah. The key is on Wednesday lecture. Yeah, we will cover the breadth-first search and depth-first search in more details. Yeah, then path, talking about the maze, you definitely got the path. Then when you find a path is a sequence of distinct vertex, each adjacent to the presenters. Yeah, so this is called a path. A to B, B to D, then D to C. Yeah, this form a path. Yeah, so it's a distinct vertex. There's no repeated. Yeah, A, B, C, D, all you only visit once. Then each adjacent to the presenters. Yeah, so B, the previous one is A, C, the previous one is D, D, the previous one is B, B, the previous one is A. Yeah, A, B, D, C. So not surprising, you got 4 vertex. So you have 4 vertex. You got 3 edge, 4 vertex. So the relationship should be the E plus 1 is the number of vertex. So cycle is just add one more. You will complete a loop. Yeah, then become a cycle. It's a path containing at least 3 vertex such that the last vertex on the path is the same as the first one. So 1, 2, 3, 4, 1, 2, 3, 4. So number of vertex equal to number of edge. Yeah, A, B, D, C, then back to A. In this example. Okay, called a cycle. Yeah, so that means here they not considered this one as a cycle. Yeah, this one not considered as a cycle. You need at least 3 vertex in the definition here. Okay, well, maybe some book they're trying to set so. Yeah, like this thing there's no, just someone today I define in this way. Generally people define in this way. Yeah, due to the letter theory, they need to use assume that there's no two vertex form a cycle. Yeah. So an undirected graph is connected if there's a path for any vertex to any other vertex. Yeah. Then when we said a directed graph is strongly connected if there's a path from any vertex to any other vertex. Yeah, so yeah, when you find a graph, yeah, you always can pick any vertex, then to any vertex you can find the path to reach there, to reach any all of them, all the combination. Yeah, that's when they are connected for undirected graph. When we said in the directed graph, we said strongly connected. Yeah, that's when it's like always there's a path from any vertex to any other vertex. Any that's when I pick any point, any vertex, and then another vertex, any one of them. Yeah, always correct. Must be make sure always correct. Yeah. So a graph is cyclic if it contain one or more cycle. Otherwise, it is acyclic. Tree is one. Tree is one of the example. There's no cycle. Yeah. As long as you can find one cycle, that no longer a tree. Yeah, it's a cyclic graph. So a complete graph, this one already explained earlier. Yeah, have n vertex is a simple undirected graph that contain exactly one edge between each pair of these things. So the maximum, the number of edges will be this. So for strongly directed graph, the number of edge is VP2. What is VP2? Okay. Yeah, application, I think there are a lot. Like earlier already explained to you that the MRT network is a kind of a graph. Your Google Map, they're trying to help you to search all these shorter path. Yeah, they need to form a graph, a map trying to form a graph and then trying to help you to find the shorter path. So in chemistry, all this, this is not my area. Okay, so it's also kind of a graph. Computer network, or electrical circuit, all this, people working on this kind PCB, they need to optimize the circuit. Actually it's a graph problem. How to squeeze all the component into this area, the fixed area, the fixed certain size, it's an optimization problem. Then to solve this optimization problem is a graph problem. You find that eventually it's a graph problem because you've got so many components. You want to move one point to another point to this point. How to position your item in the best location such that you can get the best circuit. Sometimes they need to use some simulation to simulate it. All this is you find that at the back end, they are using a lot of graph. It's a lot of graph problem. So I think these two probably I will cover on Wednesday. How to represent the problem is like the graph is not like a tree. Tree you can declare a link sometimes a link nodes with a two link. Because every nodes always have two. Binary tree always have two. But you can see that graph have a problem. Some got 4, some got 3, some have 1, 2, 3, 4. This one got 2. This one only have 1. Some got 1, some got 2, some got 3. How do I declare a prototype, a data type for me to create a graph is a problem. So we have 2. Okay, maybe this thing I will cover more detail in Wednesday together with the breadth first search and depth first search. One is the adjacent metric, one is the adjacent list. One is using metric form to represent this particular graph. The other one is using the linked list to represent this graph. Okay, so I think Wednesday I will cover. I'm trying to slow now. So Wednesday we can cover more details about this graph representation and breadth first search and depth first search. So implied that likely next Monday, I still need to cover the breadth first search and some queen problem. Add queen problem on next Monday and Wednesday. Okay? Let me see just now got any question. So for strong graph, the number of edge is V per meter. Stronger graph, back to just now this thing. If you have a strong connected graph, not really. This one is here to here to here to here. Then I need to make sure this guy can reach here. I don't have to. So this one, these nodes, you can go to the nodes 2, no problem. Nodes 1 go to nodes 3, no problem. Yeah. Then nodes 2 want to go to 3, no problem. 2 want to go to 1, also no problem. From 2 to 3, 3 to 1. 3 want to go to 1, no problem. 3 want to go to 2, no problem. Yeah. So number of edge 1, 2, 3, 4. 4 only. You have 3 vertex. Yeah, no right. So one counter example. Per mu 2. No right. 3 vertex. I just need 1, 2, 3, 4. 4 edge. It's good enough already. Yeah. Because as long as the definition is like, as long as I can find a path, doesn't mean I need to directly reach the particular vertex. As long as you can find a path from A to B, yeah, in between you visit who is not important. Yeah. You also don't have to directly reach that particular vertex. As long as you can find a path, there is a path. There is a path. Yeah. Okay. Yeah, later I will adjust the deadline in case someone didn't see it. Yeah. Probably this thing, many people not interest. People interest is about the deadline. Okay, that's all today. Any question? Yeah, I think I later after I adjust the times, I will make an announcement because look like not many people watch the video also. Yeah, but let those people attend the live section have some advantage. Know this news earlier. Okay. If no further question, I will stop today's streaming. Okay, goodbye.